In this series of talks, we're going to look at the application of mass spectrometry with particular reference to its use in drug discovery and medicinal chemistry. For this first talk, we will look at the importance of ionization, charge, and isotopes. So what is a mass spectrometer? It's an instrument that measures the mass, or more accurately, the mass to charge of a sample. The measured mass can then be used to determine the elemental composition of a compound, and it can also be used to obtain information on its structure, although it's relatively limited in this role compared to NMR spectroscopy. Perhaps the main use of mass spectrometry in drug discovery is in quantifying drugs and analytes in a variety of biological matrices. A combination of speed, sensitivity and specificity make it the main technique used in this respect. Before we continue, we'll look at the basic components of a mass spectrometer, as shown in this cartoon at the bottom of the slide. Firstly, the sample is introduced into the mass spec, where it's ionized in the source region. The ions are then transferred into a mass analyzer, where they are separated or sorted in some way. They are then detected and recorded. The basic information we obtain from a mass spectrometer is a mass spectrum. This is a plot of intensity on the y-axis against mass to charge on the x-axis. This is a spectrum of verapamil, the structure of which is shown here at the top left-hand corner of the spectrum. And it's used as a reference compound at Dundee in the DMPK department for microsomal and hepatocyte clearance assays. The molecular weight is 454 and the main ion that we see is at 455. This is due to the addition of a hydrogen ion to give the protonated molecular ion. There are a couple of smaller peaks at 477 and 493, which are due to the addition of a sodium ion and a potassium ion respectively. Perhaps the key point to note from the spectrum is that the compound must be ionized to be detected. This is summed up by the acronym NINA. If it's not ionized, it's not analyzed. There are various ways of ionizing samples in mass spectrometry. However, electrospray ionization is by far the most commonly used in drug discovery and medicinal chemistry. It typically involves the formation of adduct ions, so in positive ion this would involve the addition of hydrogen, sodium, potassium or ammonium ions. And in negative ion often involves the stripping away of a cation, such as the proton, to leave an N-H- ion, which is the molecular weight less 1, or the addition of anions such as chloride or solvent additives such as formate or acetate. If we zoom in on the molecular ion region of verapamil, we see a series of peaks of increasing mass but decreasing intensity, which we've labelled A, A+1, A+2, etc. The peak at 455 labelled A is the monoisotopic peak. The formal definition of this is that it's the sum of the accurate mass of the most abundant isotope of each element present. This is a bit of a mouthful, but in general, for medicinal chemistry and drug discovery where molecular weights are under 1,000 Daltons, generally the lowest mass peak in the isotope cluster is the monoisotopic peak. The various isotope peaks are separated by one mass unit, and this is indicative of a singly charged ion. And in the next slide, we'll look at the effects of multiple charging would have on the isotopic pattern. One other point to note is the way the data is displayed. In the purple, all the data points are collected and shown. This is continuum or profile mode. It has the advantage that the peak shape is recorded, but the disadvantage, particularly with high resolution instruments, is the file size, which can make data processing slow and unwieldy. It's possible to convert each peak to a single XY point. This is called centroid or stick mode. The intensity of the peak is positioned on the y-axis and a perpendicular drop to the x-axis to give the mass to charge. This has the advantage of greatly reducing the file size, particularly as a threshold can be set and anything below that threshold discarded. The mass spectrum of verapamil showed a number of singly charged ions, but it is possible for a compound to be multiply charged. For small molecules of less than 1,000 Daltons, this is relatively uncommon, but it becomes of great importance in proteomics and the analysis of macromolecules where molecular weights are much higher. In order to demonstrate the importance of charge, we've generated a theoretical spectrum of verapamil, assuming it consisted of singly, doubly and triply charged species. If we concentrate first on the singly charged species at m over z 455.3 and we zoom in on the molecular ion region, we can see the isotopes are separated by a mass unit as seen previously. If verapamil were doubly charged, that is the addition of 2 protons, we would now have a mass of 456.3. That is verapamil at 454.3 plus 2 hydrogen ions. But with the 2 charges, it would now appear at 228.1 on the mass to charge axis. If we repeat the process with the A plus 1 isotope, we would now have a mass of 457.3. That would be 455.3 for the A plus 1 isotope of verapamil plus 2 for the protons. So it would appear at 228.6 on the mass to charge axis. If we zoom in on the molecular ion region of the doubly charged ion, we can see that the separation between the isotopes is half a mass unit, which is indicative of a doubly charged ion. Again, for the triply charged ion, we have a mass of 457. That is the molecular weight of verapamil at 454 plus 3 protons. Now with 3 charges we divide by 3 and it appears at a mass to charge of 152.4. Doing the same for the A plus 1, A plus 2 isotopes, if we zoom in on the molecular ion region of the triply charged ion, we can see now that the separation between the isotopes is down to 0.33 of a mass unit. One thing to note is the mass resolution, which is discussed in the next talk and is in effect a measure of the peak width, needs to increase as the number of charges on an ion increases in order to be able to distinguish the isotope peaks which are closer together. To summarise, the charge state of an ion can be determined by the mass separation of the isotope peaks. The isotopic pattern of a compound such as verapamil can be explained by looking at the isotopes of the element that make up that compound and their relative abundance. The table here lists the common elements seen in drug discovery compounds and their stable isotopes. The 2 main elements that make up organic compounds, carbon and hydrogen, have contrasting effects on the isotopic pattern. Hydrogen consists of greater than 99.9% one hydrogen with a barely perceptible trace of deuterium. Even a relatively high number of hydrogens has little effect on the overall isotopic pattern. In contrast, the carbon-13 isotope has an abundance of just over 1% and multiplied by the number of carbons in a compound is the main contributor to the A plus 1 isotope, as we'll see in the next slide. There are a few other features to note on this table. Nitrogen-15 has a relative abundance of 0.36%, but the comparatively low numbers of nitrogen in a compound when compared to carbon means it usually has little effect on the A plus 1 isotope. In a similar fashion, oxygen-18 has a relative abundance of 0.2%, but again has little effect on the A plus 2 peak unless the compound contains large numbers of oxygen. 2 of the commonly used elements, fluorine and phosphorus, have no isotopes. The 3 elements highlighted at the bottom of the table have a distinct A plus 2 isotope. 32 sulfur has a relative abundance of just under 95%, and 34 sulfur just over 4%, and a single sulfur gives the isotopic pattern shown highlighted in the red. Whilst it's not always straightforward to determine if a single sulfur is present, the isotopic patterns of both chlorine and bromine are very distinctive. Chlorine has 2 isotopes, 35 and 37 chlorine, in a ratio of approximately 3:1, giving a pattern for a single chlorine as shown highlighted in the green. Bromine again has 2 isotopes, 79 and 81, which are of roughly equal intensity, and a single bromine would give a pattern as shown highlighted in the brown. If we go back to our original spectrum of verapamil, it doesn't contain any of the prominent A+2 elements, so what could be determined from the isotope profile if we didn't know the structure? It's not often that cookery can be mixed with mass spectrometry, but in a similar manner to the way in which a contestant on MasterChef might deconstruct a dish, such as a creme brulee, so we can deconstruct the isotopic profile of verapamil and look at the effect of the individual elements on the overall isotope pattern. If we first of all look at the pattern of verapamil itself, the A or monoisotopic peak is set to a relative abundance of 100%, the A+1 isotope has an abundance of just over 30% and the A+2 just over 5%. We'll ignore for now the remaining isotopes. If we look just at the contribution of carbon to the overall profile, and we had a compound which consisted of just 27 carbons, the isotopic pattern would be as shown. The relative abundance of the A peak again set to 100%, and now the A+1 isotope of around 29% and the A+2 around 4%. These figures are very similar to those seen in verapamil, indicating that carbon is the main contributor to the isotope peaks. Generally, the A+1 peak in organic compounds is predominantly determined by the number of carbons present. Although there are 39 hydrogens, the relative low abundance of deuterium means it has almost no effect on the overall isotopic profile. Similarly, nitrogen and oxygen are present in such low numbers that they again have relatively little effect on the overall profile, although 18 oxygen has a small effect on the A+2 peak. We are interpreting the profile of a compound with a known elemental composition, but if we didn't know the formula for verapamil, what could be determined from the isotope pattern? A quick look at the A+2 isotope indicates there's almost certainly no chlorine or bromine present. The A+1 peak of just over 30% indicates the number of carbons is somewhere between 24 and 28, certainly no more than 28, as this would give more than 31% as a relative abundance. The A+2 peak at 5.3% is very similar to that seen in compounds with 24 to 28 carbons, indicating there's no sulfur present, as this would give an A+2 peak of over 4% just on its own. If there are between 24 and 28 carbons, the maximum number of hydrogens present is less than 50. Although not determined from the isotope profile, the nitrogen rule in mass spectrometry states that a compound with an even molecular weight contains 0 or even numbers of nitrogens. If a compound has an even molecular weight, it will have an odd protonated molecular ion, or M+H ion. In this case, we have an M+H of 455, indicating that the compound contains 0 or even numbers of nitrogens. While this doesn't lead to any great insight into the structure, it is useful as a means of helping to establish the elemental composition of a compound. By limiting the elements and numbers of atoms, the number of possibilities can be greatly reduced, as we will see in the next talk.